Hello, everyone. Thank you so much for joining this workshop. My name is Saed, Saed Saed, and as you can see, my educational background is in medicine and biochemistry. But I'm a professor in the data science. For the last 25 years, I was just working in the AI, machine learning, data science. And since 10 years, for the last 10 years, my focus was joining data science with the omics data analysis because I found it's very difficult to write codes and then maintain it, share it, manage it, all those things. Really, we have huge amount of data, omics data, but using R, Python is not that much efficient. Then before the first step, I'm going to give you the role of data science, and then I connect data science to biomarker and why understanding the data science is important for every bioinformatician, biostatistician, data scientist in this field, and why we need to implement not just the algorithms, but also we need to implement processes. What is data science? Data science has two pieces. One is data, one is science. Data comes from measurement or from counting. Measurement, we call them numerical data, and counting, we call them categorical data. For example, temperature is a measurement, race is a counting, and gender is counting. Blood pressure is a measurement. And numerical, sometimes we change numerical data to categorical data. We call them binning. For example, we call the age, young and old. Sometimes we encode categorical variable to numerical variable. For example, changing yes to no to 1 and 0. There are other sources of the data. We call it textual data, images, and sound. In fact, all this data has a connection to the basic data type. For example, textual data is just this is, for example, a series of the numerical data in the biochemical lab information, right? Sodium concentration and the other one. This is called numerical data. But if you look at this textual data, which is from a doctor, textual data is the mix of the categorical data. Also, there can be numerical data. It's a combination of everything, but you don't treat them as the numerical data. It's the mix of everything of what when we use them to write a report. That's an example of textual data. And an image data is like this one. Again, if you look at the data in the computer, it's a pixel. And a pixel is a number. Then it's a numerical data. And also sound, for example, heart sound. Again, if you save them, is a numerical data. But what's the main difference between the basic data type, like numerical, categorical, and textual, image, and sound? It's the pattern. Then this data, there are numerical or categorical, but at the same time, they have a pattern. For example, this X-ray, you see a pattern. You see something like a heart, or you can see the lung here. Then that's the reason they call them unstructured data. But in fact, there are data which they have pattern in that data. The second part of the data science is the science part. Before data science, we had data mining. And the reason we have data science mostly because they created a degree in the university and they say, okay, we change it to data science, it's much easier. Then there is no difference between these two. Before data mining, we had machine learning. And before machine learning, we had AI. And then machine learning is using, if you can teach machine to do something, right? AI is simulation of human intelligence. Do we have such a thing? No. Most what we see it in those everyday magazine, really, they are mostly fake news. Intelligence, we don't have any clear understanding of human intelligence. Then artificial intelligence, again, is we are trying, in fact, first to understand the meaning of intelligence. But anyway, the practical aspect of what we've done in that AI and ML, we use in data science. Before AI, we had statistics. Before statistics, we had math. And before math, we had measurement. Then mostly data science, this is, for example, a math is about certainty, right? It means that for each X, you have certain Y. For each input, you have a certain output. The statistics is about the uncertainty. For each input, you have an output with some sort of the distribution, uncertainty around it, which we use probability to define that uncertainty. Then math plus probability is what we have it in statistics. And AI, machine learning, all those things is the mostly, plus we have the many models in statistics, which we use it in data science, but there are some specific type of the modeling which really they invented in the AI field, like neural network. Mostly they are iterative techniques. And then data science is about explaining the past and predicting the future. We explain the past by exploration, and we predict the future by modeling or predictive modeling. Exploration is all about the statistics. We do the univariate and bivariate analysis. We do it on the numerical data, on the categorical data, or the combination of numerical and categorical data. We can also do the multivariate analysis. PCA, TISNI, all is about multivariate. You can add it. I make this one simple. If we do this bivariate, univariate, we're going to be in a good shape. Modeling is about the supervised modeling or unsupervised modeling, which is about if you want to teach the model, build the model, and we tell the target value. For example, we have a data set about Alzheimer, and we build a model to predict Alzheimer at early stage. Then we build a model, but we give them the output based on the historical data. Unsupervised learning, there is no target. We just try to find the different natural group in our data. We call it clustering or segmentation. Supervised learning, if it's numerical, we call it regression. If it's categorical, we call it classification. This is what, when I teach data science, I call the data science in one slide. And in fact, majority of what we call it AI, machine learning, data mining, really is data science. It means it's about the exploration and predictive modeling. This is something which is missing in bioinformatics, in omics data analysis, biomarker discovery, PRS model building, is process. I strongly suggest, based on my many years of experience, even for the smallest project you have, you follow the 6 steps. And that can help you not only to build a model in the proper way, but at the same time to manage multiple projects. The first step is the problem definition. When we start with the question, we don't want to just go and explore some data without having a question, right? But when to understand the question and to understand the success, how you want to measure success, you need a domain expert. Then at the level of problem definition, if you're the domain expert, it's okay. If you don't, always ask a domain expert to help you to understand the question, the need, and also how at the end you're going to measure success. The second step is the data preparation. The majority of data right now in this field, in the genomics field, is a text file. and it takes huge amount of time to extract them, to maintain them, and at the same time, everybody has its own version, and then they use it and forget it. That's the image. Then it's so important to have data in the proper platform and manage it, maintain it properly. Otherwise, you need to do it the same thing again and again. Before doing any modeling, predictive modeling, you need to understand your data. You need to explore your data. The data exploration, at least we need to do it univariate bivariate analysis. And in many cases, I've seen it in my professional life, which they spend 6 months. At the 6 month, they see the data is wrong, or the data is majority is null. That's so important. You do, before any modeling, you do data exploration. For sure, the modeling part is the fun part of the data science, machine learning job, but I've seen many people in this field, they jump from data to the modeling without going through the proper exploration. Modeling, as I said, we're going to talk about modeling. I mentioned about the different type of modeling. But as a general rule, always start with a simple, mostly linear model. And if you see if the model is not good enough, then go for the nonlinear iterative model. That's as a general rule. Evaluation is key. We need to make sure we use the proper evaluation method. Every project has its own need. Every question has its own way of answering, but at the same time, its own proper way of evaluation. Regression model, they are not that much difficult because it's a numerical data, but classification model has many methods of the model evaluation, and each of them has its own weaknesses and strength. Then you need to understand which one works for you. And at the same time, evaluation is not just about data science part, data mining part, machine learning. It's also about the field you are using. For example, you can have an excellent classification model, but it's not going to have any value in predicting the stock market. 99.9% prediction doesn't mean anything in stock market. Then it's based on the domain you are using. Your evaluation method is also is key here. Deployment, even at this stage in our field, in the genomics, bioinformatics, it's not. We are not that much concerned about this one, but at the end, in the future, when really we need to deploy this model in the real life, we need to understand 3 levels of model testing. For example, if you want to deploy it in a bank or a financial system, if you don't do it, you can easily lose your job, and because you can just create a big problem and system stops and they lose millions. Then, but this is at this stage not that much important for us. But I'm going to explain it because I'm sure in the future it's going to play a major role. It's going to be about the life and death of the user. Okay, these 6 steps in data science, this is what we call a solution. It means when we have a problem or question, we need to have a solution. That's a reason usually an experienced data scientist or bioinformatician, biostatistician, these people, they need to have some plan. For sure, this plan is going to be adjusted, but it's important to have this 6-step plan. This is going to be a solution. Problem definition. For example, I'll give you one example here. I say, I want to build a classification model using a novel combination of the serum microRNA for detecting breast cancer in the early stage. This is a problem I have. You can use different wording. It's not that much important how you want to explain it, and it's not about the writing contest. It's just make sure you have a clear understanding of the question. And then say, okay, the criteria of success. What the success criteria, right? What criteria? I'm going to talk about more about, because the classification, we can talk about ROC chart, we can precision recall, FDR, gain, KS chart, SI chart. You may, I think you haven't heard that much about SI chart, but this is something which is going to be very valuable for our field. Okay, data. There is a link. There is a tons of data in the public domain. One of them is the GEO website. If we look at this link, if you look at this link, right, this has been done in 2016, and this is the data coming from the NIH GEO website. Okay, and this is a title for this data. There is 1,280 breast cancer cases and 2,686 non-cancer. Easily, you can see this combination is close to 4,000. The cost of just doing the lab is $4 million. And now think about, you have more than 1 million this type of the samples just in the public domain, right? And almost 600,000 just in the GEO website. And say, if I have this question, at least for the first round, I can use this type of data. You can use a simple R code to extract this data. When you extract this data, you see close to this data model. Data model is essential, and what job they have done, and I really appreciate, I should say, this is one of the best job they have done related to the managing this data on the GEO website, is the creating this data model. I change it a little bit. You can see it in the on the GEO website. You have the expression data. It means when you have the patient, you get the blood, plasma, or serum, you measure microRNA. This is a concentration, right? Then this is in the expression data. Target data, the sample, is the different type. Is a cancer or normal patient? Is it male or female? Age? That's a target data. It's about the samples. But also, I suggest you separate the genes or probes, because sometimes you need to add more information about your probes and keep that information. And you cannot go to the main data sample, this expression data, and add more columns. That makes your data model ugly and difficult to maintain. Because I've been teaching database for data science for many years, I can tell you this, following this data model is essential. Okay, if you are alone, even as a single bioinformatician researcher, I suggest you have your own database. If you are using only text data, for sure you need to manage your data. It's difficult, but if you can find an app which it can help you to manage data in a database, is better. But at the end, data management is essential. This model you see we are using on the platform in a BioLab, and because we transfer all the text data to the database and then through the ETL process, this one is crucial for improving the overall data analytics cycle. I'm going to show it this one. But again, data management is essential in data science. Data exploration, always do the univariate analysis on all your variable and probes. You say, okay, how about if I have 10 million probes? SNP data can be 2 million, 1 million, 4 million. Do I need? No, you don't need to do all those things on the millions of probes, but select subset, or I can show you, you can try first to do the density plot. That also is bivariate analysis. At least do the bivariate analysis against your target. Is your target is the cancer, yes or no? You have the uh, two cases. Just use it against your target, and that's important because sometimes you see a lot of the um, bad data, or the distribution is very unusual. It's good to see it. As again, if you have many probes, you can select a subset of them and look at the relationship between your target and probes, or those probes. This is what I call a density plot. Always do the density plot. It means your expression data you have, use the R package. This is not a simple job. And for example, this data is GS is 73002. You see there is two samples, GSM, this number, which is very unusual. Then you know you need to exclude them. Then rule one, before using your data, omics data, always plot the expression using density plot function. When you remove that two, now this is the distribution of the density plot for the breast cancer cases. As you can see, I'm not using here the normalized version. I'm personally against normalization. We need another session to talk about the problem with normalization. But you have your right. If you believe you need to normalize it, just there are tons of library to normalize your data. And this is a normal breast cases. Then I'm going to show you when we use our platform, I'm going to show you the univariate bivariate examples. Then just be patient. This modeling, always you need to divide your data to training set and test set, because we have too many probes in many cases in the omics data. You need first to find a way to do the variable selection. You need a subset of them. Some techniques, for example, they can try to do it behind the scene, but I don't suggest this one. Don't do the black box variable selection. There are tons of the statistical techniques which we can use it and find the 10, 100, 1,000 top probes. But you need to do it on the training set. It means you cannot use all the data and get your top N probes and then divide the data to training and test it, or doing the cross-validation and build a model. That's absolutely wrong. You need completely separate this one. First, they use training set to find your top 10, top 100, any number, usually this is a lower number. Then you can build your model based on the using training set, and then test it on the test set. Because we don't use test set in the training step to find the top end, then it should be okay for us. Then for modeling, as I said, always we use the linear model first, and then we go for nonlinear and iterative models. And for example, I just show you example in the real life cases. We use random forest. By the way, I have the linear at the end, but this is a random forest, and this is the best subset of the probes here, and the accuracy is 98%. This is the gradient boosting machine, like XGBoost is the same family, 99%. This is a top end. This is a deep learning, which I don't suggest to be used in this field. The accuracy is 99%, but we don't have any way of finding the top variables. And this is a linear model. This is LDA, linear discriminant analysis, which I really like it. And also we can use logistic regression. Using this model, we found just one probe, which can explain 99 with a 99% accuracy. Then always we suggest you use, the linear model first. Now, when we compare the model, again, the model evaluation techniques, I'm going to show it in our code and also then. But when we compare it, you can see it, the accuracy almost the same with these different techniques. The probe importance, variable selection, the only thing is deep learning, we don't have any way to decide about it. But linear model has a very unique feature. You can easily implement federated learning in the linear model because they are linear. You can join them or separate them. The incremental, decremental learning can be done directly. But here, using nonlinear model, you need to use the ensemble method. It means it's not an easy and straightforward method here. Model deployment, as I said, is not critical right now in the omics data analysis, but we have 3 levels of model testing. The first level is when you build a model, you test it yourself. That's the evaluation part. But you need to have a test platform. You have some production in the company which they want to use this, for example, Grail company, which they have the new test for the cancer. They have production server, for example, but they need to have a test platform as well. First, to be testing the mimic the production server. Then, not the model, another team called QA team should test the model or what you want to deploy. The reason here is there is not going to be any bias in this process. And at the end, on the production server, you need to have the capability of A/B testing. A/B testing means simple. It means you deploy the model in your production server. Now you have a new model. That model is A. You have a new model called B. Now you want to deploy B. You cannot just go there and remove A and put the B on, because always there is a chance of error, and suddenly the whole system is going to crash. You need to have some infrastructure, software, which manage with, you have a not say 90% A, 10% B, then 50% A, 50% B, then 100% B, 0% A. Anything happening in this process, you can easily change the knob to the A 100%. But if you don't have that feature, you're going to be in trouble. Okay, in summary, have a solution architect in your team, implement data science 6-step and be religious about it. Have a clear understanding of your question and problem with the help of domain expert and how to measure success. Own the data. Data is your reserve currency. If you don't want to become bankrupt, always make sure you have full control of your data. Always do univariate and bivariate analysis. Don't forget A/B testing. Choose the right ML toolbox. Thank you for this is the first section, and if you have any question, please let me know.
Thank you so much. That was really very, very informative. I'm looking into the Google Doc. I don't yet see a question, except one about the platform. It seems not to be responsive for someone. If you let us know what's the problem that you're having in the platform, in the chat, that'd be good, and we can relay that to the technical team. If you got a question about the talk itself, please do post it in the chat. And please do sign up to our Studio Cloud. So we're gonna, in the next section, do the practical part. Make sure that you have a free account inside our Studio Cloud.
Okay, now, and please connect to the this R Studio Cloud. We go through that 6-step process, but using R code. And you can just select this R code, ISCB.R, and you can see this code here, right? And if you want to run it, let me know. We can go step by step. Otherwise, I can use my local machine, which is going to be faster to do it. But if you want to run it, because sometimes you need to, there's going to be missing library and you need to install it. Batul, what do you think?
I think go ahead with the local machine. I think it's better to be more safe. Yeah.
Yeah. Okay. This is the same code over there. When you have time, you can go through the code directly. Sometimes you see you need to install the other libraries. That's the headache in the R. But for sure, we can just select this one and run it. Yeah, it's already. There is one package library called Lima, which you need to use the biomanagement, bioconductor. If you work in the bioinformatics field, you know bioconductor. But I don't need it at this stage because I think I have a Lima here. Okay. The first step is data preparation. And I have data in my local machine, but you're going to have the data on the R Studio Cloud. We just go to upload the data. Okay, you see there is the 100 samples with 9,480 probes. And then this is a target data, which is related to the sample. And I can go to just show you here. You can see it. This is expression data. The sample, GSM, each sample is here. And the probes is here, right? Then we have the target data, which is the GSM, that the sample is here. This is a target. There is two target here. Is the Alzheimer's disease and mild cognitive MCI. Right? And also there is age and gender. And also probes, which is just that. Okay, this is our data. And oh, sorry. Okay. The first step is univariate analysis. Then the first thing we do is just get the expression data, density plot. Based on the size of your data, sometimes it's going to take a few minutes, but this one should be. Yeah, this is a plot. This is a density plot. As I said, it's important to have density plot. Then we do the univariate analysis. And you see this is the 50%, 50% on the one of those target variable. Use visualization as much as you can. For numerical data, for categorical data, pie chart, bar chart. For the numerical data, you can use the box plot. They are very valuable. This is the summary for data. And this is the distribution data for numerical individual one. Then by changing the name, you can change it. Now you can see writing code is going to be very time consuming if you need to do it manually for many of those variables. The second step is the bivariate analysis. For example, if it's a numerical, doing the correlation analysis is good based on number, or you can use the plot. Sorry, I know maybe some of you have a lot of knowledge, but I just use this one as the template. And for the categorical variable, we need the crosstab, and then we can plot the crosstab. You can see there is no big difference between the gender proportion in the two cases, mild and the control. So I said Alzheimer's, no, normal and MCI, mild cognitive cases. Then for the crosstab, if you want to do the statistical analysis, we use the chi-square test. As you can see, p-value is 1. It means there is no significant difference between two groups, the proportion. For categorical numerical data, we use box plot. It means this is a categorical data, which is our target. This is the distribution of the our variable, which is, for example, here is P0001 something. This is our variable here. And this we compare these two. If you want a statistical test, t-test is the useful techniques here. Then based on the p-value, we can decide. If the categorical variable is more than 2, then we can use analysis of variance. Okay, after this part, we can go for the multivariate analysis, which is very important for omics data. And the one we can go for it is the PCA. As you can see, with this PCA using principal component 1 and 2, and this is a label for two groups. As you can see, linearly they are separable. Then it means you should be hopeful to have a good model to separate these two groups. Also, we can plot the number of the principal component. As you can see, almost with the 5 or 6 principal component out of close to 10,000 probes, you can explain the variability in your data. And the one which we use a lot, t-SNE. t-SNE is a bit time-consuming process. Yeah, again, on the t-SNE plot, you can see these two groups is linearly separable. That's the good news for us. Then we go to the modeling step, predictive modeling. And here we use first the logistic regression. But before doing logistic regression, we don't want to do it blindly on the 10,000 probes. Then we go for the step of the variable selection. Here, we can use t-test to do the variable selection because the target has just two values, normal and MCI. And then I use the t-test. As you can see, I'm following that 6 steps. That's the key. Yeah, now we see t-test selected. This is a top 6. And the number one is this variable. probe. Now I select this probe and go up at the bivariate analysis, categorical numerical, and I change this variable to this top variable and see why this is a good variable. Now you see this is good because these probes has a completely two different distribution, separatable distribution, close to normal, but they are completely different average. They are, then t-test has done a good job. And then after selecting that top, we can use some of those variables. For example, here I use 3 top variable to build the logistic regression. And then it says gain is 1. It means it's a very good model. Then if we just select the print the model, this is a model, this is the intercept, this is the coefficient for the first variable, coefficient for the second variable, and coefficient for the third. We can use it in the logistic regression model. And then we need to do the model evaluation. Again, I use the whole data in the first step just to show you if you don't want to do a modeling, for sure you can use everything for analysis, for exploration. But when you start to build a model and do the model evaluation, you need to use sample. It means you need to create divide, or I suggest you use because you need to use the training for your top 10, you separate and don't use just the cross-validation. Doesn't make any sense. Otherwise, you don't have any clue about your top N probes. But at the same time, you can not use that top 10 from the previous step because we use all the data. Then here we follow everything. It means then we get the sample here divided to the train and test set. And first we get the top of the top N or any number we want only from the training set. Right, this is the one. Now, based on the data we have, we build a model. This is our model. Now we use this model for testing, but testing is going to be done only on the test data set. Okay. The first thing is the confusion matrix. As you can see, the sensitivity is 1, the specificity is 1. This is a very strong model. There are many other components in it, but you know them better than me. And then we can use the ROC chart. Which for sure is going to be complete. And we can get the area on the curve, which is 1, which is obvious. Then we can use the gain or lift chart. I'm going to explain this gain and lift chart in the demo because I don't like this type of the chart in R. Then let me explain it but gain and lift chart, when you translate that gain and lift chart to the decile chart, it's very valuable. That's the one important missing part of the model evaluation in bioinformatics in this omics data analysis. Then we go to model evaluation here. Now this time we use XGBoost, which is the version of the gradient boosting machines, a nonlinear, very well designed and with high performance. But really, we don't need to do it here. I just put it here as the template for your practice. Okay. Then we use the test. Same steps here, which you have the confusion metrics here, sensitivity, specificity, positive predictive value, negative predictive value. Same thing for the chart and the gain chart. Yeah. Okay. This is the steps which, except the deployment, the first 5 steps, this is a template. And we can use this template for other problem. But you see the problem here. For every changes in my data or my question, if I want to focus on the just male or female, or if I want to change it, the model, or I want to input, add or remove some of those probes, I need to go inside the code. Maintaining this code is difficult. Okay, this is the one. You have this code, as I said, in the cloud, ISCB cloud, and you can run it by yourself. Any question, any comments, or anything, if you have done it before, you had past experience, do you agree with me about this difficulty, or you have, did you have any solution for it? Please.
Well, I don't see comment about that, but I see comment about other things within the practical. If you want me to, that's a good timing for us. So we have someone commenting, I'm very, very impressed with the practicals, very, very well delivered and understandable. And someone asking, what is the case against normalization when making density plots?
Yeah. Normalization, when you do the normalization, the good news here is the predictability power of your model is not going to change, but the correlation between your probes is going to change. It means simply, if you use raw data, you have ABC as your best probes. If you use the normalized version, you have XYZ. It doesn't make any sense, right? And if you use the other data, for example, if you use a credit data, which makes sense, you have those data is understandable. When you normalize your data, suddenly the relationship between those variables you see, there is no meaning for it. This is one. The second part is when you normalize something, then when you normalize it based on rows and columns. If you have a new data set, you have a data, you normalize them, you have a model for predicting cancer. Now you have a new cases. How do you want to normalize it? You normalize that data based on the previous data. And you cannot easily use this raw data against normal. You have 2 options. Keep all data in your database, then you have a new one, put the new one in the raw data, normalize everything, and then predict it. There was some silly solution in other field for it. Doesn't work. And based on my experience using up to easily thousands of this omics data, you get the same quality of the model using non-normalized data. And normalization is going to change the relationship between probes. Also, is not going to be easy to use it for new cases. You cannot use it except just mix them together. Is that clear? Yeah, I can show you this one example if you want to see it. Then there's, say in the financial system, we have a credit data coming from different group, different people. You have the FICO score. That FICO score is coming from people from the US everywhere. Do we normalize them? No, we never normalize that data. I know there is many source of the variability in our data, in omics data, which is a big problem in reproducibility of the same data. But normalizing that data is not the solution. It's going to add another layer of complexity to your data. Okay.
Thank you so much
Sure.
for the elaborate response. One more question. What advice should be followed when setting a threshold of significance?
For which one? For the p-value or for model evaluation?
I'm
Which
not
one?
sure. So if the participant can, so both, it says.
Both?
Yeah,
Sorry,
that's
what
what
was?
participant asked.
Okay. Yes. You know, honestly, uh, there's two different things, right? If you are talking about the p-value for t-test, they have the false discovery rate rule, right? Because then you have 50,000 or a million of probes. Certainly, you find some of them randomly, which is going to be better than uh, chance. But when you repeat the test, you completely lose those previous probes. Then I think you should follow that FDR rule. If that FDR rule of 0.05 is a good one, and you simply divide your probability level by the number of your data points you have. And but sometimes, honestly, sometimes that rule doesn't work. But we don't have any other option. As a base, I believe that FDR 0.05 is a good option. And but at the same time, there is nothing written on the stone. And I can show you in practice how you can manage this one. But as I said, just use the common sense of using that 0.05. On the modeling side, maybe you're talking modeling, even when you build a model, now how you want to, for example, one of those things is ROC, right? Uh, that ROC chart is a tricky chart. I've seen even in the in the public domain, you see the paper or research, even tests they are using. They say we have ROC of 0.7 is much better than 0.5. Doesn't make any sense. 0.7 can be completely useless. You should understand what question you are trying to answer, and if you get some result, what's the practical use of it. I'm going to, as I said, I'm going to show it by example, and you get a better understanding. Okay. Now, what we are doing in Biota Lab is building uh, a platform which we can make the whole life easier from all that 6 steps. Even I have, yeah, I have a little bit of time. And just while we are building this platform called Biota, what happened? Okay. There are more than 1 million omics data samples available in public domain. Example, GEO, Array Express, Broad Depth Map, TCGA, UK Biobank, ADME, more and more. But and we have if the number of the bioinformatician, biostatistician, data scientists, they are limited. And easily 80-90% of people in the life science, they cannot use it, and they need our help to do it. We need to change it. We cannot just wait and for the other teammate to do some of those jobs which can be automated. Then our goal was to create a platform which that other 80% people, with the help of that 20% of the experts, they can speed up this process of analyzing data, building PRS model, finding biomarkers. That's what's the goal. We try to implement all these 6 steps. For example, we do the project management. If you build a model, you start a project for Alzheimer's, cancer, you can keep it in that platform, and then you can maintain it. Then it plays as a project management. Also, we move data from text file to the database. That gives us huge amount of the improvement in the next step of the managing data and also doing exploration and modeling. Instead of writing code, we created interactive visualization and statistical analysis. We always need bioinformatician, biostatistician, data scientists, but now we improve the whole process 10 times, 100 times better. Then instead of waiting for the whole team say, okay, we can spend instead of 1 hour, 10 minutes to do the same job. Modeling also can be done interactive, and if we use linear model, federated learning is going to be much easier to be implemented. Evaluation also can be done interactively, and visualization. We don't need to write the code, go back and forth. Even for deployment, when we build a model, we should be able to automatically generate the code, and that's can be done behind the scene. Then Biota helps everybody in this life science related to the omics data, transcriptomics analysis to improve the productivity. Biota platform is simple. There is one component which is the take care of the data and data preparation, exploration, and modeling. The backend data goes to the SQL server, and ETL process takes care of the data transfer. It can be a single user or it can be a multi-user. Now, what I've done it on RStudio, I'm going to use Biota. This is Biota Smart Array. Here is your project management. Right now, there is nothing in this project, right? Then the data I have here is the same data. This is the ETL process. This is the expression data, probes data, and target data. We saw it. We don't need to repeat. We just transferred during the ETL process. Now this data is going to go to the database. This is also goes to the database. And now we send now this is a data expression in the database. Now I have my data set, that experiment here. I can add all the information I need here. I put the subject, title, URL. I put the node. I can completely manage it. If I have the same data, for example, the normalized version of this one, I can easily create another project and put it here and keep track of the normalized one. that's going to be, honestly, this is going to be as important as any other feature we have here. The next step after I have data ready is the exploration. Oh, sorry. Okay, now I have a data. I can use my univariate analysis. For example, I use the age. If I want to do it the histogram version, I can do the histogram version. I can use the gender, right? I can use the target here. I can use the different. The goal here is at least I should be able to do 80% of what I need without asking any external help. And then I can do the bivariate analysis, target against age, because I want to know if there is a significant difference between age in these two groups. A little bit significant, right? 0.05. And then that's what we know. You can easily see this is the percentage of these two, the blue, and this is the average of the age in these two groups, which is on the right side. This is the frequency for the blue on the left side count, and this is the average on the right side. This chart, I call this one MVP, the most valuable plot for data analysis, because you can understand the predictability power of your variable as well. You can use gender. It's automatically understand this is both categorical and uses the proper plot and also test. It uses chi-square test. You can see there is no difference between the percentage in these two groups. Also, I can go and select the probes. This is a probes, concentration of probes in these two groups, and I can change it, but for sure I don't want to do this one by one for almost 10,000 probes. Then the second step here is I can go to the top end and ask the program to do the same job, but automatically for all 10,000. As you can see now, you see the plot, the volcano plot here. There are tons of good probes. Everything is red and blue are good. And also this green also sometimes they are good. That's the limit based on the FDR 0.05. And but again, we can ignore them. It's good just as a base. Okay, now what I have here, I see the variable. Now you see now the chart here, this average of these probes in normal cases is much lower than the mild cognitive version. And then I can use the bar chart. The error bar chart is just 3 standard error of mean. Again, you see completely separated. And now you know a linear model can easily separate these two groups. Can I go directly to the modeling? No, because I use all the training set. It doesn't work this way. We need to separate them. Then I'm going to use the random number to separate this 80%, 20% cases. Now I only use 80% for training, and then 20% I leave it alone, put it aside just for testing. Now here I have a subset. Honestly, I only need 20. Top 20 is top 2, even top 1 is enough. But when I want to save it, I just remove this check because now I want to save everything. I'm going to save this data here. Go back here for modeling. This is a quick modeling version. In the platform, we have another separate toolbox, which is a complete federated learning component is part of it. But for this one, for that 80% of the people in this field, this is going to be a quick way of building model. Now you have a choice of selecting model selection option again, or you can just, this is a powerful model. Then this is the model, this is the coefficient. You go to predictive. You see the learning is based on the 80%, and testing is 20%. This is the overall, the accuracy, precision, and recall. In the confusion matrix, you see there is just one mistake here. There is only one mistake. And now you see different charts here. This is a gain chart. Gain charts, which means every 10% of population, you expect 10% of target. Now you have 20% of target. It means twice better than the random model. For the left chart, the same thing is going to be translated to the ratio. There's 2 times. 10%, 20%, 2 times. You saw this one in R code, the last part. You saw this one. But the R code doesn't have a good gain chart. I tried to find it, but I couldn't find it. Case chart also is important because it shows you where you see the maximum separation between 2 groups. Here, the maximum separation starts from a score from 0.1, goes to 0.8. It means everywhere you can separate this one. An ROC chart, which is 0.98 here, and the area on the curve is 0.98. There is one chart which is missing in our daily job in bioinformatics for this omics data. It's the decile chart. I strongly suggest you understand the role or learn how to use it, because decile chart, it tells you, it's based on the gain chart, by the way, but decile chart tells you if you have an accuracy of your model overall 80%, but based on if you use a subset of that data, that accuracy can go to the 95%. Then by having a threshold on your score, you can change the accuracy of your model. For example, if you look at this one, if I say this is 2 groups, I divide this one 2 groups, 50% lower score, 50% upper score. That nine cases out of 10 cases is all in the upper score. It means if you use the average score, anybody out of 0.5, you have a strong belief that person has an MCI. Again, sometimes you don't need to use this amount. You go to the decile 5 and you say, okay, I only choose those scores which is more than 0.75. The rest, I don't decide about it. But anything after that point, I'm going to put the decision. It means you don't need to make a decision based on the area on the curve, which is related to all the data. You can just focus on the specific group. Say, my decision is going to be related to this specific group. And then instead of say, if I have a score more than 0.75, I'm going to make a decision. Anything less than I don't make a decision. Suddenly, your average model is going to be a strong model on a specific group of those patients with some range of the score. Here, you can have the other way. It means you say anybody which has the less than 0.1 score, they are not going to have MCI. Right? Here, I put a limit of 0.1, for example. Why it's important? Because now you say they are coming to the clinic, there are 1,000 patients. Majority of them, they don't have MCI. You say if this patient has the less than 0.1, he can go. We don't need to detest it. What percentage you are cutting? 40%. 40% of patients coming to your clinic, this model can just cut them, rule them out. because you know there is a 0% of chance they're going to have the MCI. This is I have another session just talk about the role of decile chart with a different example, but I strongly suggest you work on the decile chart. It has a lot of useful application, and based on my experience in this field, majority, they easily say positive predictive value for everything. What's the positive predictive value for all the population? Why? We have using the score in many places. Based on the level of the score, we make a different decision, right? Then that's the way we should do it here. We don't need to focus on the whole pie. We can make, say, only on some specific part of the pie, we can make a better decision. At the end, we have a script. This program, this platform easily generate the script you need in the SQL code or Python code or Java, C# or VB, anything you want. You can just use this code to implement. You have new cases. You can just put the input and get the output as the score for your patient. This is the one quick example of how you can find your biomarkers and how you can build a PRS model using that biomarker. Any question on this?
We have just one quick question about the platform itself, because it looks very interesting. Yeah. So they were asking, is it free? How do you use it? Yeah.
Yeah, we are, right now we are giving it for free, but you need to have it on we suggest to have it on the cloud system. You just need to have a server on the cloud, AWS, Azure. It should be Windows-based platform right now, but it doesn't matter on the cloud. You can have Windows, Linux, anything. And then you need to contact me or another colleague, which they can help you to just deploy. It's some sort of the package which you can deploy it on the cloud, but it's better to be a cloud server, easy to. I don't suggest it on the local machine. You can have, I have it on my local machine, but cloud, because you can share it, it's much easier to take it off the cloud. Then you can make an image of it and use it. Yes, you can have access to this one, but we suggest to have a cloud server first.
That's incredible. Thank you.
Sure. Okay. Any other question? Now, the important aspect of using the issue of the normalization, because we use the normalization a lot. By the way, just before this one, I can. This is our website, and besides we explain the products here, this is a biobank. It means using this platform, we analyzed so far hundreds of the public domain data. If, for example, if you go here, you see the link, and also you see the biomarkers. If you see green, it means this is a good data. You can try it and see some value. You get some value if it's related to your research. Yellow, it means we don't know. It's good, bad, really, we are not. Red, for sure, they don't have any value. This is based on our analysis. And there is a lot of data related to the cancers and more, you can go to our website. At least if you have a question, you can do the search and find something useful. And now this is a lot of data which we analyze in last few years. I go for the one very interesting data. Psoriasis. If I have time. Okay. You know, this is a GSE, which is a normalized version. This is same data, expression, probes, and target data. And if you click on the target, is about the three what they sample. One is the involved skin cases with psoriasis, normal from control, they don't have psoriasis, uninvolved skin for the psoriasis. It means you have a psoriasis cases and the normal case. On the psoriasis cases, you have two samples, one from the lesion, one from the non-lesion area. This is a very good data set. There are, psoriasis is one of those diseases which we have a lot of good data about. And if you look at the distribution, you see this is a distribution of data here. This is a normalized distribution, right? Now, if I go to the another psoriasis data, use the normalized version. Now, they used a different method of normalization. And if you go to, and this is true in many cases. This is one problem with normalization. You cannot, when they say normalize, you should know exactly what they are doing. Okay. Now, I use this data. I can go back here. This is our target. You see, ultimately, we add a random variable for the sampling. And also when you need a random. This is the probes and the genes attached to these probes. Now you see behind the scene, the ETL process is sending the data to the database. But at the same time, because this is the 50,000, 54,000 probes, we cannot have a table with the 54,000 columns. We can do it in the NoSQL, but NoSQL database system has their own problem. Then we use a technique called sharding. The users don't see the technique, they see it as just one table, but behind the scene, the Biota manages those tables. Okay, now I have my data experiment here. Double click. Okay, this is my target. There are three different targets, but I only want to use the normal skin and involve the psoriasis one. Then I go to the filter. I say only use these two. Then this is the relationship between the two groups and different probes, right? You can see this. I don't want to use it for modeling because there are tons of the good probes and there is no value for modeling here. We are not looking for the predicting if it's psoriasis or not. We just want to understand the change in the genome. Okay, now I go for the top N. As you can see, there is tons of the good variable probes here. And even the one score of 17 here, score means 17 standard deviation. It means between these two groups, if you go for this one, they have 17 standard deviation separation between two, which is huge. Okay, you see the probes here and gene, name of probe and the genes. If you double click on this one, it directly goes to the gene card. You can see about the information about this gene. And usually what I suggest is going for top 200 for analysis, for enrichment analysis. And you can call this one normal and lesion, LS, normal against lesion. And you can save this. I don't want to analyze 50,000. There is no need for when I have top two. Top two is that much powerful. Okay, and then I go on the enrichment part. And I have an option to select any number here. You can select top 10, 20, top 50. For example, I can select top 50 of this gene and do the KEGG pathway analysis. Then you can see the pathway here and see which pathway has the higher, and amazingly, you see biases. Okay. We proved in another research, which this is going to be one source of the one trigger for the psoriasis. You can do the use reactome pathway analysis. You can use the gene ontology. You can look at the chromosome. There is a simulation, which is, I need another session to talk about simulation, how you can simulate the behavior of the genes. Another very interesting part is the drug repurposing component. For this one, I just look at because I want to know is the upregulated or downregulated. I just use the upregulated one. And I use top 20 or top 50 only upregulated genes here. Then you click on the drug repurposing. It's the gene and drug interaction. And then you see up. It's amazing, right? There is 50 upregulated genes in psoriasis. Nickel atom can upregulate 35 out of that 50 without downregulating any genes. And we know nickel is the number one heavy metal allergen, right? This is amazing. Now I go for the just downregulated one. As you can see, there are not that many downregulated genes in the top 200 of the genes. You can go back here and instead of only select the top downregulated one. And you call this one down and save only 100 is more than. Now you can go back here. You say, this is a downregulated one. All of them are downregulated. I select all 50 and click on this drug repurposing. Again, you see nickel atom downregulate 32 out of 100. Sorry, out of 100, only 2 upregulated. Now you see this quick analysis gives you a point which you can really start to, without too much external help. We can help that 80% life science researcher, practitioner, to do something which they can do it without our help. And when they need our help, then we can go on that 20% extra which we need to help them. Okay, this is the analysis which we can do. This is some part analysis. We have the correlation analysis as well. But I want to show you the problem of the normalization. Even this one is one of the best data set, which we have a good overlap between normalized and non-normalized. Okay, this is a raw data from same data set, but this is a raw data. Yeah, you see it's not normalized. Raw log, because when you look at the just raw data, you see there is a long tail, which is not good. Okay, then I go back here. I go through the same process. Now you see it's take 30, 40 seconds. But you see why I call Bioda as a project management platform. Because now if you have different version of the same experiment, right? The normalized version, another normalized version of the same thing. Mass is using mass 5. Raw data, raw log data, just using gene ontology version of it, just using the pathway version. You can just combine them and use the pathway method of just the translate, map the gene to the pathway and build a model based on path. All this different version, you can have it in your platform and manage them in your platform. Now I have this one. I go the same process here. This is target. I only want target for normal and I get the bivariate analysis. Then if you have more than 2 value in your target, Bioda chooses the ANOVA automatically. This is again, you see tons of the good predictive probes here. Okay, I'm going to use the same name here, 200, like the previous beta. I save it. Now I can go to the experiment, use the multiple GS. GSC, this is just the series of the name for the tape. I have this 200 here, and I have another. Now I want to see the overlap between these two. By the way, this is the best data set which you have. You see a good overlap. Out of 200, you have 111 overlap between two. It means less than 60% overlap between two. Not only this one, you see, this is, by the way, this is one of the best overlap we have. The problem here is correlation changes. It means now if I use this table here and see the correlation between different, between these probes and other probes, right? This is this probe, which is the PI3 gene, and with this one, and with this one. There's a different correlation. This correlation, when you normalize them, this completely changes. That doesn't make any sense. We need to know which one is true. Is the correlation based on the raw data is true, or the correlation based on the normalized data is true? My analysis, which I have a presentation for it on my GitHub, the account, I showed if we use, for example, other data which we understand, like credit data, when we normalize them, the correlation doesn't make sense. Based on that analysis, I believe the normalized data fakes the correlation, which is not really meaningful in the real environment. Okay, that's all on my side. Thank you so much for your time. If you have any question, please feel free to send me email. And
Yeah, thank you so much.
this is my email, which you can contact me for any further question. Any question for?
More question from Albert. He's asking, can I use your model, apply your model to mosquito RNA-seq data to investigate the resistance for biomarkers?
Yeah, you can. This platform is for microRNA, RNA data, RNA-seq data, protein array, SNP data, methylation data, but it's not for the raw sequence data. The only things we don't do it is the raw sequence data. It means when you just sequence them, you need to change it to some sort of the meaningful relationship to your target. That's it. It's the same thing we have. As I said, we have 1 million plus samples. That's it. That's the only things. You should, if you can follow the format we have in the Geo website, that's going to be the ideal one. Then if you want to upload your data in the public domain like Geo or Array Express, even you have it on the web map, you need to have the data in the text format, which you have the sample, the information about sample, and information about your expression data. That's all. That's all you need. But it can be coming from anything: RNA-seq, microRNA, protein array, SNP data. You can, but if you have, for example, 2 million SNP, for sure your server should be a good server, right? You need a bigger server. That's all.
Amazing. Any more questions? Don't be shy. Take this opportunity to ask a question. We do have time for questions. If you don't want to add it to the chat, you can add it to the Google Doc. If I don't see any questions.
I see one question is related to the other, is if it's not human. You mentioned this one, right? But I see a mosquito or something. It doesn't matter. The only thing is your data should be in the proper format. That's all. It doesn't matter it's coming from which type of the species. Okay.
Yeah, and someone asked some technical question about the code in RStudio and installing the packages, and I was so happy to see someone else answering the technical questions as well. So that's very good.
Those questions you can have it on our biodot.com platform. You can see the installation process, which is very straightforward. That's usually if you have your Microsoft ready, the Windows platform, it's not that much different.